coming. Not okay.
Good afternoon. Welcome to this colloquium of PRL today. We have a speaker, Dr. Bhaskar Mukherjee from the University of Sydney in Australia. He's going to talk to us on radiation dosimetry and radiation protection in space missions. A very exciting topic indeed. To introduce the speaker and conduct the proceedings, I will request my colleague, Professor Devabrata Banerjee, to please introduce the speaker. Professor Banerjee.
So, good afternoon, Professor Raju and others attending this PRL colloquium. So, I'm pleased to introduce Dr. Bhaskar Mukherjee, who is a former colleague of mine. He's presently affiliated to the School of Physics of University of Sydney, Australia, and he's also had he's also connected with the University Helmholtz Institution, Radiation Medicine of Helmholtz Institution in Munich, Germany. So after obtaining his bachelor's degree, so at the physics, he studied physics at the Technical University, and then he has pursued. So he's an associate scientist at the Institute of Radiation Medicine, and after obtaining his bachelor's degree in electrical measurements and instrumentation from Jadavpur University, he studied physics at the Technical University of Berlin, and then he received his BSc, MS, and PhD degrees, specializing in nuclear physics. He has pursued postdoctoral research at several laboratories at the Argonne National Laboratory in Chicago, Michigan State University, then Meson Factory in Vancouver, Canada, the Austrian Research Center, Siebersdorf in Vienna, Austria. Sorry. So he has had a very he has a lot of experience in building instruments, and has held senior positions at various research centers in the USA, Australia, Austria, and Canada. He has also published more than 200 research papers in journals and reports, and has been credited with 6 patents. So he's specialized in various fields, and radiation biophysics is a favorite. He has championed the cause of luminescence dosimetry, particularly for human space missions. He's also, of course, a reviewer of many journals and an associate member of space research in COSPAR. So he is an expert on radiation dosimetry, and today he'll be talking to us on radiation dosimetry and radiation protection in space missions, a very relevant topic in light of the fact that there will be a manned mission in the near future. So I hand over the podium to Dr. Bhaskar Mukherjee from the School of Physics, University of Sydney, for this presentation.
Thank you. As I said, I belong to Germany and Australia, and my topic of my presentation will be space mission, radiation dosimetry, and radiation protection. First slide, please. Next slide, please. Yes. I would first divide the scope of this talk. The structure of space is the first point. The structure of space belongs to the main topic of the work. It broadly made of 4 layers. And between the space and inner atmosphere is separated by Kármán line. The second point will be the dosimetry. The dosimetry locations in the four spheres: the troposphere, the mountain, as well as aircraft heights, in stratosphere, the balloon, and in ionosphere, in outer space, the ISS. I will discuss all these topics, which is highlighted by ellipse. But to have not mentioned, I will also discuss the effect of radiation in particle therapy. High energy particle therapy has got very similarity like space radiation. That's a medical application, and I will discuss broadly in my talk. The second slide, I just basically depicted the type of space radiations. And you see the left side, the highlighted with gray, which is all stopped, and right side is our net space radiation experienced by missions as well as in nanosatellites, where we have got only electronics. Next slide, please. I will first talk about the balloon, because balloons are the forefather of space travel or space radiation measurement, not aircraft, not rockets, but balloon. Because balloon people studied the effect of cosmic rays and discovered cosmic rays. This is the first balloon ever, hot air balloon ever mankind used, that is in France. It is famous siblings, Joseph and Jacques Montgolfier, two brothers. And they have got the hot air balloons. And you will see lots of hot air balloons nowadays everywhere, but not with open flame. They're using gas mantle and gas torch. And all the tourism, the balloons are hot air balloons, the principle of Montgolfier. Next slide, please. Now I'm in Sydney University, left side. You will see the old building of the Sydney University and the first balloon in the Victoria Park, which is an integral part of the Sydney University. It took place in 1871, January 21st. On the right side, I will show you the present Sydney University main quad. Actually, it is built in 1854. So the picture left side, the building is only 17 years old. This building is holy temple of knowledge for us, kept as new, and it is still, people take conferences and classes, mostly humanities and political sciences. And below, it is our physics building, built in 1925. So it is still, I walk there when I come to Australia, right side and the basement. So this is the physics building, and the left side, the historical picture of the ballooning in Australia. Next slide, please. India was not lagging behind. The first balloon in India balloon flight took place in Calcutta, 1889, and the gentleman was Ramchandra Chatterjee. His typical Bengali name will be the Sri Ramchandra Chattopadhyay. British name is the Babu Ramchandra Chatterjee. And this balloon he built his own balloon, which is all written there, city of Calcutta. And I took this picture from the Chronicle of Asiatic Society of Bengal. Right side is the balloon, the woodcut, and the left side, the news flash in this Asiatic Society of Bengal. And the background, I'll just try to show the Calcutta in 1989. So that's the historical picture. And this Ramchandra Chatterjee used several types of balloon flights. And he also jumped from the balloon using parachutes. And he died in a normal age, so he lived quite long. Next slide, please. Now it is a real invention of cosmic rays by balloon. It is in Austria, in Vienna. It's Professor Victor Hess. He used the balloon. The first time he has used hydrogen gas filled. The balloon I showed in Calcutta and in Sydney, it was coal gas filled. But Dr. Hess used first time the hydrogen gas filled. And 1912, which was prior to the First World War, England and Germany and France, they tried to develop blimps, that is the lighter than air aircrafts for war purposes. So balloon was already quite developed. Professor Hess used such a balloon, And he has taken an electrometer with him. This electrometer is called Wolf electrometer. It has got no electronics, no power supply, no microprocessor. It's the most sensitive electrical device to measure the cosmic rays. It is very astonishing. It has got no power supply. It is made of quartz fiber, and I will discuss later because it is still used in space dosimetry. Right side on the top, how we landed in a hamlet in Austria, how received by kids. He treated like a Santa Claus. And the right side below, that's the most important picture. It is the discovery of cosmic rays. You can see the radiation dose of electrometer currents is first in x-axis, that is the radiation is coming from the natural background radiation from in the vicinity of Vienna. That's mostly granite, very high radiation dose from natural background radiation. Balloon is rising until 1 kilometer above ground. This natural background radiation drops, which is very logical, 1 by r square practically. You're away from the radiation source, and radiation intensity drops. But after that, instead of dropping, the radiation is increasing drastically. So at 5 kilometers, it was quite high. It is absolutely 4 times higher than the ground radiation. So Professor Hess concluded that radiation is coming from space. And he used the name Höhenstrahlung, that's a high altitude radiation in German. But the cosmic radiation, cosmic ray, the term coined by Millikan and Carl Anderson, 2 American scientists. And Professor Hess later migrated to the United States. So he is the father of the cosmic ray. He discovered cosmic ray as well as space radiation. So as I said, the space radiation is first detected using a balloon. Next slide, please. We followed the footsteps of Professor Hess in Sydney University, and we started some balloon expedition. And 19th of July, 2015, that is Australian winter, European summer. And we launched the balloon. Now you can see the left side, the map of New South Wales, and the inset, the map of Australia, map of New South Wales, and the white spot is the West Vyalong. That is our balloon launching spot. And the coordinate is given, right side, elevation about 214 meters, ground temperature 12 degrees Celsius, which is quite cold. We have used winter. The story is that when balloon lands in a remote area, in summer, in Australian bush, infested by snakes and spiders, it's very dangerous to fetch the balloon. So we deliberately started the expedition in winter. And instead of electrometer, we developed our own pin diode detector. And that right box, it was the balloon's launch time, landing time, retrieval time. It landed 11:30 and we retrieved 4 p.m. And balloon has reached the altitude of 30 kilometers. And below picture right side, you see the GPS track of the balloon path. So we followed this balloon with our Land Rover to fetch the balloon. So it is our first mission. Next slide, please. This is our second mission in 2017. We did almost in July. We did that because solar maximum is solar state of solar cycle is reduced. So we are reaching solar minimum. And as usual, solar minimum produce more radiation, more cosmic ray, higher cosmic rays. That we'll show later and discuss later why solar minimum produce more cosmic rays. And this gondola has reached about 162 kilometers, far, far away because of the wind condition. And all this picture, A, B, and C, A is the balloon launch, B and C are the picture taken by the balloon. I will come later. The balloon has got a very sensitive camera, Very cheap camera, but it's very sensitive. And you can see this B picture, the white spot, that is our Land Rover, where we started our balloon. That's our location. And these are the real pictures taken by balloon. And the right side, you will see when the balloon landed, and the white box is our payload box, which we retrieved, where we have got our detector system. Next slide, please. It is the electronic system that we developed completely ourselves. TCV, that's a radio modem. GPS is GPS. MCU, that's a microcontroller unit. SD card, lithium polymer battery, and watchdog timer, WGT. And right side, we have got all the detectors, external temperature, internal temperature, accelerator module, and GG, the gamma detector, which we have developed ourselves. Right side, you can see how the gamma detector looks like. It is coming from the medical physics, but we wrap this detector with 0.2 millimeter of lead, which will compensate the cut off the low energy gammas, and the response will be flat. So detector will be almost gamma energy independent. Left-hand side lower picture showed you a very informative picture. At 30 kilometers altitude, balloon bursts. When the balloon bursts, the fragmentation of the rubber, the neoprene rubber, the balloon, it's illuminated by light, sunlight. So the space is completely dark after 20 kilometers. Sunlight is there, but it reflects from the ruptured balloon. You see the dynamic of the balloon rupture. And it took the selfie picture, 11:20 GPS time. We took that. And the right side, lower picture shows how the sky look like. Sky is blue. You see the wonderful atmosphere. You see the clouds, and the sky is black. Later on, I will show you a picture by ISS on Mir, took the picture of Earth exactly like this. So with our humble balloon of 30 kilometers, we photographed the space picture just like Mir and Space Shuttle and ISS. And you can see the pictures of the cloud and the thin blue line of the atmosphere. And I like to say, we also try to get the picture of the aurora borealis, because aurora australis, but southern hemisphere, we have got aurora australis, but we have to hunt for the aurora. We didn't get it. So we have to make many balloon flights to see this aurora. Otherwise, we have seen some green light on the top of the atmosphere, but we have not seen. But one day we'll get aurora picture for demonstration purposes. It is not that we have devised a method, an algorithm, how to calculate the energy of the aurora by comparing the light intensity of a green laser. It is the next topic. Next slide, please. These are the results. These are the parameterized results of the cosmic ray components. On the left side, you can see the total EPCAT is the code from the Germany Helmholtz Center. We can simulate this radiation, and below is the which we have measured with our gamma detector. Sydney University Gamma Ray Detector Sugar. We christened the name of the detector, and its gamma radiation is quite low, mostly coming from the neutrons and protons. I will show later the pilots in the aircraft, they get high dose coming from the neutrons. On the right side, our paper, which is the first paper of the balloon expedition, which describes everything about the balloon expedition, as well as the detection system and some photographs as well. Thank you. Next slide, please. Talking about thermoluminescence dosimetry, Professor Banerjee is one of the experts, but here we have done thermoluminescent dosimetry dedicated for space radiation. Top left side, all the thermoluminescence phosphor we are using, not only for space, also for terrestrial experiment. When number B, that is the Thermolox BEO, and number D, the TLD 700, which we have used for space radiation dosimetry, maybe one day also for Gaganyaan astronauts or Gagannauts. But we are using that for pilots and patients and simulated by ISS astronauts. Okay, right side, you will see the principle of thermoluminescence. This thermoluminescence phosphors, quite unstable, and if it is irradiated by radiation, ionizing radiation, electrons split from the atom lattice and captured in the electron trap. At the same time, a hole trap arises as well. And this configuration remains unchanged. So that reason, we can say the entire radiation information is stored in the TLD phosphor. When we heat it up, the right side in the first picture, the trap and electron recombines and you get TLD photons. I have seen only one trap and one photon intensity, but there are many traps. You get many types of photon intensity. There's the TLD glow curves with many peaks. Left side, second picture, that is a TLD reader I have constructed, copying a similar detector TLD reader system, used by Mir. So my colleagues from the Hungarian Space Agency supplied me all this document, very simple to construct. It worked out very well. And we have measured the TLD of americium beryllium, TLD spectrum of americium beryllium neutron source. I'm just using americium, pure americium alpha source, not neutron source, no beryllium. Americium alpha source has got 4.5 MeV alpha line, as well as 60 keV gammas. And you can see this glow curve right side, low temperature peak, it corresponds to the gammas. I have not seen the corresponding trap transition. There were two traps. There's a low temperature trap, and the right side, high temperature peak, the high energy trap. This belongs to alpha particles. I'd like to show, and this is result presented below. The deconvolution, we have developed our own method how to deconvolute the TLD glow curve. So TLD glow curves are overlapped. By deconvolution, we can separate it and correlate with different types of radiation. In here, alpha particles and gamma rays, and we have used very simple readout system, very robust, but it has worked out very well. Next slide, please. Now, this is a work we have done in Michigan State University, large superconducting cyclotron, K500, K1200 superconducting cyclotron, entire facility 110 meters long. I would like to say this K500 cyclotron is now constructed in Calcutta, VecCal or Baba Institute, excellent machine. So we have now the capability of heavy ion with high energy particles in India. But that time I will come by later. I tried to construct experimental setup in Calcutta, but it didn't work out because cyclotron was still in the commissioning phase. Right side, the partial view of the K500 cyclotron. Left side picture, TLD irradiation port. We have used the TLD irradiation port, which is actually used by NASA people to check the radiation hardness of electronics components. It is now possible in India, we can test all the electronics components we are using in space shuttle, or even in the military, radiation hardness. We can test this in Calcutta cyclotron. It cannot do that low energy machine. Many people have Van de Graaff accelerator, and they have some wishful thinking that they can use low energy accelerator for testing of hardness testing of electronic components. It is not possible because space radiation is much high energy. Below right side of the two glow curves, this time we have used very sophisticated TLD system, actually TLD readout system, which Dr. Banerjee's group has in PRL. We have the same thing in Australia, one place, and Germany, we have several. So you can see this TLD glow curve, left side, that's with krypton 56, with charge state of 20 plus. It's a very high energy, heavy ion. You cannot attain that in a Van de Graaff accelerator. And you can see the glow curve, two bumps in the high temperature region. One is TLD 700 and one is TLD 600. TLD 700 is lithium fluoride with enriched lithium 7, and TLD 600 lithium fluoride with enriched lithium 6. Right side, we irradiated this two detector in our Prince of Wales Hospital. I did an ANSTO actually in leukocytes with gamma rays, and we evaluated the glow curve. You see there is no high temperature peak for gamma. Now we take the ratio between TLD 600 and TLD 700, the 0.667 for krypton irradiation, and for gamma irradiation 0.725. It means TLDs are actually not so sensitive to high energy radiation, but more sensitive to gamma rays. Again, these results was highly comprehensive. We published, and we also used that for the iron 26. The iron atoms are very prevalent in space. So if you do the space radiation with cosmic rays, not krypton, we have to try with iron or with helium 4. So, but it was a first test run, and later on, my colleagues of NASA, they used this facility to test the electronics, and it was Michigan State University when I was doing my postdoc. Next slide, please. I'm coming back to space radiation, space station. 1929, I'm talking about Germany and my alma mater in Technical University of Berlin. Most of the space research took place in Germany and in Berlin. There was a story. 1918, Germany lost the First World War. It is called Weimar Republic. Germany took the very high reparation cost, the Versailles Treaty. Not supposed to do any research in space, in aircraft industry. Germany is not supposed to build an aircraft, but there was no clause against rockets. So all the German scientists, not scientists, they are amateur people, they started to building rocketry, and all took place in Berlin. Our university, my alma mater, Technical University of Berlin, and a famous lad, Werner, he's called Werner von Braun, who was student in our university. And there was a plethora of journal, popular science magazine, popular science presentation about space research. Right side, you see a picture called Frau im Mond. It's a film you can see on YouTube. In English translation of the Woman in Space, Woman in Moon. You can find it now, audience, YouTube. You can download this film. It is subtitled in English. Frau im Mond. Left side is a picture of a rocket. It was a dream of Werner. Later on, Saturn VI he developed. Right below, small picture, the Rakete, the rockets. And you see this simple picture and this circulating path of there was no satellite, and it was all conceptual drawing. And there was another very famous guy, Walter Hohmann. He was a civil engineer, but he was an amateur astronomer. And he created orbit transfer mechanism. As you know, the Chandrayaan and Gaganyaan, they sent to space with a very small rocket, the PSLV. And with this method, this orbit transfer method, it can reach a very high altitude. It can reach Moon and Mars. Even you can go to in Venus, Sukrajan. Always this orbit transfer method discovered by Walter Hohmann, and he died in 1935, 10 years after this invention. And he was a civil engineer, worked in German railways. At 1929 to 1933, it was a peak of German rocketry, and then you know the V1 and V2, all German young lad, Werner von Braun, who actually visited India in 1970s, and he also spoken to Professor Abdul Kalam. He visited ISRO when he was a consultant. He retired from NASA, So he was a consultant of rocketry. I visited India. And figure number 2 is the Skylab. It's the first American space station, Skylab 1, Skylab 2, Skylab 3. And it was real sense it is a space station. You can see the astronauts are having their meal just like a pub standing, and it is a Skylab 3. And next step of Skylab, which have not shown, it is Space Lab, which is a bigger space lab, where we have got a connection of TFR and PRL. There's a Professor Goswami and Professor, he's from PRL, and Professor Biswas from TFR, Tata Institute of Fundamental Research. They have used Space Lab to study cosmic ray using CR39 detector, the plastic scintillators. I will come back later. They are pioneering work done by PRL and TIFR by 2 Indian scientists. I was actually expecting Professor Goswami because he knows me well. And now, right side, I showed number 3, the Mir. Mir is the real space station. And it is very robust, worked very well, very long. It is international. Right side, I showed the picture of Russians and Americans. They're enjoying their time in Mir. Below is the International Space Station, ISS, still running. And I have highlighted the arrow. International Space Station is a LEO spacecraft. It orbits the Earth 92 minutes. And you see the picture with the arrowhead, 1,5 Stunden in German, 1 hour and 50 minutes in German, 1,5 Stunden. So Hohmann calculated this orbital time of LEO spacecraft. There was no LEO satellite. And it is published in the popular science magazine, Die Rakete. And ISS, they use all, not only ISS, most of the low Earth orbiting satellites are 92 to 95 minutes. Right side, I will show you the picture of ISS. The left side, the lady, she's our Sunita Williams. So it was becoming real practice, many experiments, and I have also used some data from ISS for my calculation. I will show later on. Next slide, please. This is Mir. It is a real workhorse. Left side is the Pile TLD system from Hungarian Atomic Energy Commission. And I got a compact TLD reader. It is still used in Russian sector of ISS. But early version, I got details. I've got all the sketch, and I have developed my own using this little blue box. Right side, the re-entry of the Mir. Mir was not accidentally just Challenger or Columbia. It is not destroyed. Mir was brought down deliberately. So it is not accidental, extremely rugged spacecraft. So I have got this connection with the TLD radar system, which is still used by Russian sector of ISS. Next slide, please. This is our ISS, which is still running. Right side, there is a tissue equivalent proportional counter area monitor for ISS, which my friend Edmund, he's a space radiation analysis group of NASA. He sent me a circuit diagram because this is quite obsolete, but I tried to build one using these details. It is completely open source, but I got from my friend Eddie these circuit diagrams. Now, top of the space station, you will see the large solar panels. Solar panels are also on Earth, solar farm. And these large, shiny solar panels are placed for the bird droppings. Bird likes that. Our solar panels in Earth is full of bird droppings. With space, there is another nuisance. It is not bird droppings. It is space debris and junk satellite parts, which many times collided with this this solar cell in the ISS. And I would rather like to say, I think one of our audience group will be there, It is a young space startup company in Bengaluru, Digantara. So with these young friends, I work as a collaborator. So they are using a novel method. They're using nanosatellite and wonderful software system with AI and a camera. They like to identify and classify the space debris. First stage, if everything goes well, their satellite will be launched end of this year. And there I will also send some radiation detectors for proton monitoring. But anyway, these Digantara people will be listening this talk, so I congratulate them for their feat. Next slide, please. Now I'm coming back with more details about space radiation. First picture, I just give some points, but now more details. Left side picture, which I've taken from the NASA Outreach Picture Gallery, galactic cosmic rays. Main source of radiation in space is galactic cosmic rays. Outer galaxies, it is omnidirectional. You can see the Earth with magnetic field. And galactic cosmic ray comes from every direction, never change with time, but is modulated by 11-year cycle, because 11-year cycle, the Earth magnetic field changes, the blue lines. Left side, you see the sun. This is the biggest problem, the solar cosmic rays or solar particle events. They are very sporadic, but they're mostly proton, alphas, and some high energy heavy particles. And in the Digantara satellite, we like to send a solar proton monitors, which we have worked out. Its name is Ravi. So, and if it's successful, we'll make with our own detectors solar particle events measurement using a nanosatellite. Left side below, you see this real picture, which I'd like to discuss. All these particles, solar wind, trapped electrons, all captured, not all, many of them captured in Van Allen belt. It is trapped. And when you are outside any satellite, outside any containment, you are exposed, no gray line. But gray line is very important because off the satellite and space capsule, all protected. And it is, you need very low energy particles. You see, it is all stopped by 33 millimeters of aluminum stuffed everything. The space shuttle and also Mir, the capsule is very thin, 5 millimeters of aluminum. It's not lead or not exotic material. It is very simple, very, and there's another problem. If you have the heavy material, high Z, if you put shielding with heavy material, it collides with high energy cosmic ray and nuclear reaction. It's called spallation reaction, which is pure nuclear physics. It produces many secondary radiation. So instead of shielding, astronaut will be highly exposed with the secondary radiation. So spaceships towards Mars and high interstellar expedition, they're made with very thin material. Actually, they should be made of plastic or polyethylene, not with lead, plastic and aluminum. Now, coming back, the nature of solar particle events. It is highly sporadic. You don't know when it happens. When it happens, and when it happens very large intensity, it could be lethal for astronauts. But in general, in normal condition, all the radiation is trapped in Van Allen belt. So we are protected. So radiation in the outer space and radiation in the aircraft is not much different. But there's one problem is that Van Allen belt is come very close to Earth's surface, near the southern coast of Brazil. It's a South Atlantic anomaly. It happens because the Earth magnetic axis and Earth geographical axis are tilted by a few degrees. So at that zone, the Van Allen belt come very close to the Earth's surface. So when the satellite pass through the zone, they're exposed to the trapped radiation. This is the only location where astronauts get high radiation. But this radiation is also mostly stopped by surface of the spaceship, not spacesuit, I will come back later. the gray line, and we need the minimum shielding. But worst case of radiation exposure of satellites, even in Gaganyaan, all in Van Allen belt, in this South Atlantic anomaly region. And when you go to outer space, so interstellar, even to go to moon, there is no Van Allen belt. Radiation will be completely different. And I will not discuss in details in this presentation, maybe later on in other presentation. So this is very important. Left side, real radiation coming from space, galactic cosmic rays, and solar cosmic rays, solar particle events trapped by Van Allen belts, and only exposure when astronauts or LEO satellite or LEO spacecraft like ISS, like Gaganyaan, everything passes through Van Allen, this South Atlantic anomaly region. Next slide, please. Coming back, completely different topic, biology and dosimetry is utmostly important. And this is the field which coincides medical physics and space physics. Left side is a simple picture. Everybody understands radiation dose is the energy imparted by particles in small bodies per unit mass, that is radiation dose. When the absorbing bodies are quite big, radiation dose is joule per kilogram. But when the entities are very small, just like a biological cell, dose could be very high when the impinging particle hit the cell, and dose will be very low, it doesn't hit. So it is probabilistic. When the entities are very small, radiation exposure is highly probabilistic. That is the reason radiation effect in human body very probabilistic, not determined. It is deterministic when dose is very high. It is burning with the fire, but in low dose, it's highly deterministic. And the dose depends on the linear energy transfer and quality factor. It is also people who are working in nuclear industry or medical physics is very common. So LET, linear energy transfer, is high when the particle penetrates through the cell. Right side, it can go to the DNA strand. And some of the cells are very, very highly ionizing. So it is called overkill effect. It will be hitting a cell many times. What is the optimum LET, it kills maximum number of cells. You don't know, but it is done by the microdose. I'll come later. So it is the trick of radiation with highly dense, different ionizing rate, different LET types of radiation. And sensitive site is very important. Normally it's DNA helix, but it also could be chromosome, but in model we talk about DNA. And this biological effect of radiation, it's a link between microdosimetry and radiobiology. And how the biological risk is done, conceptually thought, it is pictured in the human body. And all the numbers is the radiation weighting factor. Because the bone marrow has the highest radiation weighting factor, which is common because bone marrow is a highly proliferating blood cell. Breasts, colon, and stomach are also very high biological radiation weighting factor because all the cells are highly proliferating. At the radiation dose, or risk, which is not R is a risk, not dose, depends on the radiobiological dose, as shown in the left side, top side, whatever radiobiological dose, depends on the ionizing density of the radiation. Age at exposure, if the candidate is very young, the cell proliferation rate is very high, radiation dose is very high. Gender, women are more radiation sensitive. I come back later. Why? The lady astronauts would be more vulnerable to radiation than male astronauts, which we have proven with our dosimeter. And radiosensitivity is the organ. As I said, left side, some organs are more sensitive, some organs are less sensitive. Frankly speaking, brain is the less radio insensitive. If you irradiate a brain, nothing will happen. So it is a But problem is that eye will get cataract, but the brain is completely radio insensitive organ. Stomach is the more insensitive, and the bone marrow. So bone marrow is extremely sensitive to radiation. I have taken you something to think about this picture. So a few seconds I stop because I've explained too many things in one picture. Left side, right side, and below. The most important is the picture left side below. That is the radiation weighting factor of human body and risk. We'll be using that for astronauts modeling. Next slide, please. It is very important about dosimeter. It is valid for medical physics, space physics, for everything. It is explained by the Bragg-Gray theory of cavity. Say of the object of the radiation object is our human body, which is practically it is astronauts or patients or everybody, or even the members of the public when everybody get the natural background radiation. And the dosimeter is a cavity, it's a discontinuity. If the dosimeter material is the same Z, that is the average atomic effective atomic number, then the radiation coming, some stopper, crosser, and starter, which is all self-explanatory. Radiation is stopped, radiation starts from the cavity, and radiation crosses through the cavity. It will be not changed because the material of the cavity and the material of the body, human body, is same. But it is not the case all the time. Cavity is normally filled with different types of dosimetric material, not like human body. So cavity is not same. So radiation field get perturbed. The dose you measure with the cavity dosimeter is not the real dose. You make a huge error. To compensate that, you have to cover the cavity with a compensator. Then you can get no perturbation. But there is another hiccup here. This compensator depends on the quality of the radiation. So one type of radiation has a different type of compensator to the other. So if the radiation varies, like in space, you cannot use a simple compensator to compensate the radiation, the efficiency of your radiation detector. Left side I have summarized tissue equivalent. Tissue equivalent is the ratio of effective atomic number of the dosimeter material and tissue. It is almost 1 for tissue, water, air is almost the same, lithium fluoride, beryllium oxide, and radiochromic film. But aluminum oxide dosimeter, MOSFET, diamond detector is not the same. So people are using electronic dosimeter for space dosimetry. They are completely wrong. Not wrong, they're incorrect. But to circumvent the problem, one used the tissue equivalent proportional counter, a RAM counter. It is a 6 centimeter diameter, volume is 48 cubic centimeter, sphere filled with 1.77 kilopascal of propane gas. By varying the propane gas, you change the probability of impact of the radiation. Actually, it simulates a tissue volume of 2 micrometer. The 6 centimeter diameter sphere filled up with 1.77 kilopascal of propane gas is a tissue. So impulses coming from this after irradiation, any type of irradiation, from the tissue equivalent proportional counter, after the extra picture, which shows the mild tissue analyzer and all the storage CPU and everything. So entire information of radiation interaction is tissue equivalent dosimeter, tissue equivalence condition is saved and stored. It delivers the linear energy transfer quality factor from gamma rays to high Z particles. So it's ideal for space radiation, gamma rays to proton, neutrons, everything. But it is quite heavy and you cannot take it with inside your body. So there's a solution. Next slide, please. Very simple principle which we have developed. Actually, I have developed quite accidentally. If you take the lithium fluoride and beryllium oxide, we have irradiated with various LET field. So we simulated the cosmic ray by bombarding this polyethylene phantom with proton beam of various energies. Now we have done it in Germany, but now in India, in Chennai, the Apollo Hospital, we have the same cyclotron which we have used in Germany. So we have simulated space radiation by bombarding a polyethylene phantom rectangular with proton beam. But now quite accidentally I found the ratio of the TL glow curve, aluminum oxide and beryllium oxide, it depends intrinsically with LET. The R is the area of the beryllium oxide by area of the lithium fluoride, and the first formula is fitting. Let average is 258 ratio minus 24.8, and quality factor is 60.1 R minus 6.43, very unique, and it is correct because we checked it, worked out. And this response fits with the ICRP 123 response. ICRP 123 says the quality factor and LET relationship, and it is valid for space, human body, everything. So it is a key point of radiation protection. So this lithium beryllium microdose, it's a microdosimeter because it gives LET and quality factor. It fits in the criteria of ICRP 123. So it could be universally used as a dosimeter, microdosimeter. There's a dosimeter and microdosimeter is quite different. Microdosimeters give you risk and LET, so you can really tell the late effect of radiation using microdosimeter, not with a normal dosimeter. You have to do lots of epidemiological study for a dosimeter. The right side, it looks like this. I put 3 lithium fluoride and 3 beryllium oxide to get better statistics. It's quite simple. This system could be easily done in India. And it is quite accepted, and I applied it many occasions, which I come to this presentation. Next slide, please. First application was in Airline Pilots. And now Airline Pilots is not exposed to direct solar particle events and galactic cosmic ray and South Atlantic anomaly. Aircraft pilots, as well as balloonists, they are exposed to cosmic ray shower. When high energy proton hits nitrogen atom in the upper atmosphere, PRL is a pioneering scientist you have there. So it is a carrying coal to Newcastle. So I'm just telling, it produces lots of other particles, neutron, proton, photon, which actually used in balloon studies. I showed, you can show this balloon is 35 kilometer and aircraft is about 13 to 15 kilometer. And mountain, I will come back later. We measure the mountain as well. And these 2 pilots, it is a picture, it's not my picture because my picture is, I should not put because it is classified picture of Lufthansa. But there's 2 pilots I've used. Except the picture, all information is correct. Right side is the gray area. These 2 pilots attended in 3 months of time, visited all these locations, different heights, different altitude, so different LET particles, all different conditions. And they have used mostly Lufthansa cargo have used this as a candidate. Next slide, please. These are the results. One is a male pilot and one is a female pilot. She's 38 and he's 29. And they have carried the dosimeter. And their duration is their block time, 148 hours and 149 hours. At quite a long distance, 1.5, 10 to the 5, hundreds of thousands of kilometers they have traversed. Both traverse almost the same distance, but different altitude at different seasonal time. So their equivalent dose is different. 520 millisievert, microsievert, 550 millisievert lethal, 520 microsievert, and 327 a 737 microsievert for the female candidate, and also high temperature lithium fluoride. This is also that is calculated with the EPCAD, and we have measured with this lithium fluoride 565 instead of 520 is the calculation simulation, and 735 and 737, quite close. Average quality factor 11.0, 9.2, 96.6 is the LET, 91.9. But the female candidate I should not publish the result. She got a higher risk than the male candidate because of her gender. And right side, you will see the beryllium oxide and lithium fluoride glow curves, which we have used for this fitting. And the right below, you see the readout system. I think in PRL, you have got exactly the same readout system. We have used very sophisticated one, not the homemade one. And it has got very high repeatability. It has the internal calibration facility, but you should not consider the internal calibration facility for this purpose. For normal geological application, you need a strontium 90 source, which is built in here. But it is, if we do space dosimetry in India, we should use this readout system in PRL. And right side is our result. Some results are classified because in this paper, we should not tell the name of the candidate and what is the age I have to mention, but not the routes, flight routes, because Lufthansa will be very angry if we disclose their routes. We get on the code. You can check this paper, and we should not publish the radiation risk after the flight of these both pilots. And one personal news, a lady, I shouldn't tell her, she became pregnant and she got a baby after she completed the flight, and she was quite healthy. So I'm very satisfied, and she congratulated me that I have monitored her radiation health. It is a pre-pregnancy time, but anyway, so radiation is also somehow frozen inside the DNA. So it is still, my calculation was very effective. And it is all done with these dosimeters, which gives radiation risk. And again, the reference, I have also taken this ICRU journal, which is very important, because I've compared our results with this ICRU reference. So it's all compared with a highly recognized reference documentation. Next slide, please. Now, I mentioned the cancer risk assessment of pediatric patients. Pediatric patients irradiated the proton beam. Again, not gammas, not neuroproton. And again, in Chennai, we have exactly the same facility. This is the nozzle, and proton beam is highly conformal. So you can design the proton beam such a way it hits the tumor location. Tumor is a volume in red. It is, everything is depicted, and you have to move the gantry different angles to get the beam exactly in the tumor. But the problem is that you irradiate the tumor with high energy proton beams. Exactly like space radiation, it produces lots of secondary radiation, mixed radiation, and it propagates to the body of the patients. First patient was a 13-year-old girl. I've used a female patient because the radiation risk is much higher. And that these 4 points are the radiation, the microdosimeter I put. And the below is a very young girl. She's only a few months old. 1 year, 6 months, very little girl. And she has got a tumor, which is called skull-base tumor. But both young ladies survived. And I have measured their radiation risk. And you can see the risk of the elderly girl is less than the young girl. Right side, different location, thyroid, left breast, right breast, lung, stomach. For girls, you have got the breast and lungs in the same organ. So breast, there's a latent breast of the very little girl in the same location of lungs. So you have the lungs dosimetry and breast dosimetry. You measure the same dose but different radiation weighting factor. And this weighting factor risks model, it is called Bayer report 2006. This risk coefficient is all there, risk coefficient I have to take from this reference. It is not my invention, and it depends on the age and gender of the patient. So young girls, for thyroid, it is more than elderly girl in the thyroid. It is all depicted there. So lifetime attributable radiation to LAR risk, not dose, lifetime attributable risk. LAR for different organ we have calculated. And HT and Q we have measured with this microdosimeter, which is placed in the patient's body. And we recommend, if India we can do something, we have to do that for female patients. We have also got elderly gentlemen with prostate cancer. We don't care, 65-year-old gentleman with prostate cancer, we irradiate also a proton beam. Risk doesn't matter because most probable late effect takes place after 20 years. But if a 6-month-old baby girl come here, we have to assess the risk, because when she grows, she may go to second cancer. Second cancer is very important, not secondary cancer. Second cancer is a cancer grows independently for the primary cancer. And the secondary cancer is called, it is metastasis. If the primary cancer grows, it becomes secondary cancer. But second cancer has nothing to do with secondary cancer. It can grow after a long time and different part of the organ. And this model and this dosimeter, microdosimeter, will give this risk of any type of patients, but we have emphasized the girls, not ladies, girls, younger the worse radiation vulnerability. And this could be also used for astronauts. I'm coming back later in the next slide. Next slide, please. Just coming back, astronaut. Again, a male astronaut, female astronaut, and galactic cosmic ray and trapped South Atlantic anomaly. This cupola is made of 5 millimeter of aluminum and borosilicate glass. And you see the astronauts having just like a normal apparel, t-shirts, no spacesuit, nothing. Calculated the risk. I'm using the Cushing-Otta model, and I'm parameterized with this microdosimeter. Now, coming back to extravehicular activity. One day, maybe India will make space station, astronaut will come out of the space station, and people will get exposed. But exposure is not important because there is very little radiation. This space suit is not made for radiation safety, radiation protection. Space suit is used to protect from the high vacuum of the space and cold. So if there's a hole in the space suit, the astronaut will explode because entire body liquid fluid will evaporate and explode. It's like a balloon. So space suit is just like a bulletproof vest, not for radiation protection. But radiation protection is important for the visual, the goggles. So I get exposed with radiation, and even there is a solar flare, astronaut could be blinded. So we try to simulate the solar flare with my BRC friend in Calcutta Cyclotron. It didn't work out because of commissioning time. So we repeated the experiment in Germany, and we calculated some model to design the visual of the spacesuit. So we can design a quality assure of the spacesuit goggles using this proton beam. And we don't care about spacesuit, only visuals. And if you go to Mars or Moon, that's a different story. But normally the EVA, the extravehicular activity, spacesuit is only to protect against vacuum and debris like space junk and micrometeorite, but not against radiation. So this paper, we have simulated the solar flare. So you can simulate any solar flare using a proton cyclotron, which India has got now in Calcutta BRC. It could not be done with medical small Van de Graaff accelerator. It's a wishful thinking. You need a high energy proton accelerator for particle therapy, which you have in Germany, many places in the US, UK, Japan, and India has got 2 or 3. And the research cyclotron is BRC in Calcutta, which is 500 MeV. We can emulate very high energy solar flare with simple software and some evaluation method. Next slide, please. Now, these are the results I fitted with this ISS value. And I've used this model of Francisco Cucinotta. And the risk factor depends on the age and dose. So I have plotted lower picture, left-hand side, age and the risk factor for female and male. And I get some linear fitting. So I can fit with different age very easily with this model. And data I have coming from ISS value. And I have taken 6 astronauts, age between 55 and 25 years old. And these are real astronauts. I shouldn't tell their name in ISS. And I have calculated their radiation dose after their mission time, 300 days to 60 days, male and female. I got all this data from ISS logbook. I got the dose, and I fitted with this model, calculated risk, and the results look quite good. So if we have got a Gaganyaan, we can use this method to calculate the radiation dose. And if we have a female astronaut, it will be also okay. But we can assess the radiation dose of male and female any age. Here we have done 25 to 55 years old. And results are very authentic, coming from our latest ISS data. Next slide, please. I'm coming back to the mountaintop experiment in Germany, Zugspitze. It's a 2.6 kilometer tall. It is in Germany. It's actually our Helmholtz Center lab, their neutron lab. You have to go with cable car. Right side is the laboratory, neutron lab. And you can see the very slant roof made of wood, because no scattering. It's not metal roof, simple roof. And it is you can see my picture. I'm standing in the middle plane of the hut is the neutron spheres, and I'm just below manipulating the spheres. And one of the sphere, the red points, that is our ICRU sphere made for astronaut dosimetry. And it is a German standard laboratory for neutron dosimetry for high altitude. It is called Zugspitze. It's the tallest mountain in Germany, but not tallest mountain in Europe. Mont Blanc will be the tallest, but it's tallest in Germany, Zugspitze. I have lots of nice photograph and video, but anyway, please, next slide. This is how I model the results in the mountaintop to astronauts. Again, the middle picture is the radiation weighting factor. The right picture is the augmented ICRU sphere. ICRU sphere, you can see below this, it is standard sphere recommended by IAEA. This sphere, which emulates the human body. And the right side, left side middle is the human body. And the left side is a very sophisticated phantom by Matryoshka by ESA. It is sophisticated because they are using this phantom when the astronaut go to EVA, extravehicular activity outside the spaceship. But for inside, you don't need to be so elaborate. A sphere will do. So I have emulated, augmented the sphere to, coming back next slide, to correspond to the human astronaut's body. One slide before, please. Not this one. One before. Yes, come back later. Just next slide, please. Stop, please. And in the middle, we have the microdosimeter. We can give it to the astronaut. So this microdosimeter is calibrated with the real field which we have received from the mountaintop. We can repeat that with, coming back next slide, with particle therapy beam, but it came out also very well. So this is universally applicable in mountaintop neutron dosimetry. Next slide, please. So this is a generic photograph of conceptual, even we have got a Gaganyaan mission. First, we have to calibrate the chips. Left side picture, polystyrene phantom. We can do that in Chennai Apollo Hospital. In the middle, we have got the augmented ICR sphere. Sphere has got small holes at different depths. It will fit the lithium fluoride and beryllium oxide dosimeter, and it will be covered by a bag made of spacesuit material. It emulates a real condition. And we put that into the crew module. It should be well secured because there will be high G when launching time. It can fly away. So all this type of material will be highly secured with the body of the crew module. Crew module is also thermally insulated. So when flashed down, it is not heated. This augmented sphere, which we have designed, we can attach to the crew module. It will be launched to space. It will stay an unmanned space mission because we are studying the unmanned space mission, 7 to 10 days. It will splash down. Sphere will be removed and put into these slots of the radiation dosimeter from PRL. And we'll calculate from the glow curve, LET quality factor, and radiation equivalent dose. Left side will be the results we summarize. We get from this readout system and other formula we discussed earlier. You get the average LET, average quality factor, equivalent dose, and the gender and age specific risk. So once it is calibrated, we can issue these astronauts, or come back later, simple dosimeter. We evaluate and get all this data left side of the picture. But we have to have a crew mission, unmanned crew mission, and all the devices will be developed in PRL. So nothing coming from outside. And step by step, I discuss the flowchart. Next slide, please. This is all the status of the dosimeter. Left side you see the area dosimeter. It is the quartz fiber dosimeter developed by Reverend Father Leonhard Wolf in Germany in 1825. This Wolf dosimeter is still used in space dosimetry, also in nuclear power system, anywhere. People working in BRC, they all use this dosimeter, but it is also used by NASA or Mir or ISS, both from Russian and American section, as area dosimeter. Middle, we have the dosimeter, not microdosimeter, presently used by NASA. It has got everything, but not beryllium oxide. Right side, you see this portable dosimeter used in the Russian sector of ISS. You can see the white little box is more advanced. It is much lighter and much more advanced. On left side, you can carry these bags when you transfer from Earth to ISS. Left side, you will see this dosimeter used by JAXA, nuclear trackage detector. This detector, I said, pioneered by Professors Goswami and Professor Biswas. They were pioneer of the trackage detector with cosmic radiation dose. In the middle section, you have recently developed Orion project, next NASA big mission, Orion mission, and also ISS. It is called battery-operated radiation detector bird, but it has got disadvantage, as I mentioned, materials, semiconductors. Advantage is that you get immediately the result. Disadvantage is it is not tissue equivalent. Those will be not very accurate. Right side, I'm depicting again the tissue equivalent microdosimeter. This microdosimeter, right side, could be used to any astronauts. After we have calibrated that in proton therapy cyclotron, because this dosimeter changes the sensitivity with time. I have some calibrated dosimeter with me, calibrated in Germany, but it is not very reliable. But if we deploy this dosimeter, real human space mission, we have to calibrate again in India, very easily. It could be done, evaluated in PRL. Once it is done, we can use that for a few months because it remains. If you properly calibrate, you can store this dosimeter in a safe place, and you can use again and again. So this is the status of space dosimeter, which is really used nowadays, not experimental. It is really used by space agencies, NASA, ESA, Roscosmos, and JAXA. Next slide, please. Summary and conclusion. TLD 700, 700 and beryllium oxide, we can emulate a true gas-filled TEPC of a much larger size. I've shown a picture. It is so small, you can put that in a pocket, and you can put that in a human orifice in the body in an internal dosimetry. Non-toxic, very simple, wrapped with aluminum foil. It's a microdosimeter. It gives you average LET, quality factor, any types of radiation field. You don't need any compensator. Microdosimeter responds to any type of radiation field, universal response. And 5 to 300 keV per micron, very high LET. So it fits ICRO response for space irradiation. 5 to 300 keV per micron. 5 keV per micron is gamma rays, and 300 keV per micron, very high energy, very high heavyweight cosmic ray particles. We never get that in LEO, but if you go to Mars, we can use this dosimeter because it can respond to very high energy cosmic ray as well. Broad detection limit, quality factor 1 to 16, as I said, lead, LET average 5 to 200. 300 is too optimistic, but 200 we can do very easily. We can simulate it in Michigan State University. And very high dose, 0.1 millisievert to 1 sievert. And it corresponds to ICRP 123 recommendation. It has been validated by balloon and cosmic ray shower in Airline Pilot, validated and published. Next slide, please. The silicon on insulator, this state-of-the-art electronic microdosimeter, which is not tissue equivalent, but advantage is it is online measurement. Tissue TEP is a bit passive, but it gives very exact result. But you need exact result because you total accumulated dose during this mission and then evaluate. You don't need to evaluate every minute or every second. So it is a real surrogate of the large TEPC, and it complied the Bragg-Gray cavity theory because it doesn't need any compensator. And it could be used for lifetime attributable risk. It is not proton therapy patient, they normally one irradiation, they're completely healed. So lifetime 1, 2 irradiation, and lifetime means if very young, after 20 years, what will be the second cancer? Which is all proven by this modeling experiment. Our hypothetical study also established with the crew mission ISS and MIR. And radiological risk for astronaut is called radiation exposure-induced death, a reduction of longevity. It is not lifetime attributable risk, it is a terrestrial. It is almost the same in terrestrial condition, but REID it is for astronauts. It is model coming from NASA. Risk is higher for female astronauts than a male astronaut. We have proven already. Now, Bluefield says that this could be used for any human space mission, maybe one, and it is all components and devices is made in India. It is not everything produced domestically, and it could be used for future, any space mission, particularly from India, the Gaganyaan mission, but it could be used for any space mission. Next slide, please. it will be actually the last slide. I thanked our people. Actually, this is, I formally thanked I formally thanked my friends in Germany and students of Sydney University during the ballooning mission. And Worcester Proton Therapy Center and Helmholtz Center was very helpful for proton irradiation. Unfortunately, BARC didn't work out because cyclotron was in commissioning phase in Calcutta. And I thank you, my audience, for your attention and hearing me. And any question you can email to me. My email is there in the last line. Thank you very much. Thank you for attention.
Thank you, Dr. Mukherjee, for an interesting talk. Now, are there any questions?
I have to shout.
There are questions. So the one is from Harish, which is visible on the screen.
Yeah, so Harish is now I can see the question. Why does radiation risk depend on gender? Who is more at risk, women or men?
Women with the cell proliferation, and also women in the puberty is much more risk than women post-puberty. So elderly female astronauts has got less risk than young astronauts. Gender of a person who is more risk, women is the more risk.
Okay. The next question is by Kinshuk. Is there any study to understand the effect of radiation on astronaut?
It is already done. It is all because that is the purpose radiation dosimetry. Purpose of radiation, it will be very critical when people go to Mars or Moon, because the radiation will be very high. There is no Van Allen belt, and if there is a solar flare, it will be deadly. So radiation risk of astronauts is very important. It is already, that is the reason of the radiation dosimetry.
Yes, most of the presentation was regarding that. Naveen Chauhan is also there. He's an expert on luminescence dosimetry and he's a faculty in PRL. He's asking why TLD 600H high temperature peak responds to only heavy charged particles and not gamma radiations.
TLD 600 also sensitive to gamma rays, but heavy particles, the high temperature peak, actually if you take the bulk TLD 600 and 700, TLD 600 is more sensitive to gamma rays. But TLD 6 has got enriched lithium 6. It produces lithium N alpha reaction. And this alpha produces the peak. My first picture I showed to you, I have irradiated the TLD 600 with pure alpha particles of americium. And you can see the high temperature peak is there. In a mixed radiation, if you have got a TLD 6, it will respond to high temperature for the alpha particles, but it is very deceptive. TLD 700 is also sensitive to high temperature peak, heavy particles, because high temperature peak is high temperature peak. But the trap depth is different for 600 and 700. So I have done many work with high energy neutron irradiation using TLD 700, not TLD 600, because TLD 600 are very sensitive to alpha particles. And you have got neutron, backscatter, room scatter, it produces thermal neutron, it produces alpha particles, so oversensitive. So your dose will be overestimated by TLD 600. So high energy neutron, always use TLD 700.
Okay. Next question is also by Naveen Chauhan. It's on luminescence efficiency of different LET particles is significantly different and also depends on energy. How is that taken in consideration when you're estimating dose, of the astronaut?
It makes very. That is the reason I'm using the total TLD glow curve, not one glow curve. Total TLD curve, TLD response. People has done previously mistake. They have high temperature peak, low temperature peak, and it makes no sense. The bulk response of lithium 7, TLD 700, and bulk response of TLD beryllium oxide. At this bulk response, any radiation, because entire response is distributed inside the glow curve. So I'm not taking high, late, or low LET. I'm taking the entirely mixed radiation field. I'm talking about mixed radiation in microdosimeter. And now the more, not the energy. Energy is related to LET, and it has got a track distribution in the LET. It depends on track distribution and LET. But we are not considering that in microdosimeter, we're taking the entire dosimeter in account. That is a very important question.
All right. So, question 3
Yes.
is why OSLDs are not used for space dosimetry purpose?
Because
decay constants of OSLDs
it is done, which is
can be linked to LET. So why not use this LET dependence for predicting particle type and radiation dose?
Now it is done, which is one of my colleagues, Ramona Graza, then when he was doing, actually when Dr. Bhaskar was in Oklahoma State University. Yes, the decay curve of the OSL signal, the slope of the decay curve, you can correlate with LET. Actually, the Professor Mukherjee group is trying to use OSL dosimeter in space dosimetry, but it is not very effective because it cannot distinguish slope very effectively. But it could be done with slope. But it is not very effective. The decay constant, exactly, it is a slope. Decay constant is a slope. Yes, it is done, which is not very effective. If
right.
don't talk about, yes, sorry. In microdosimetry is not dose, we are talking about the quality factor.
Still another question. They are found to be tissue equivalent, and also luminescence is quite sensitive. Diamonds be used for dosimetry?
Yes, only for the dosimetry, for photon dosimetry, not heavy particle dosimetry. You have to compare with 2 dosimeter. And diamond has got also lots of other problems. It's highly dose dependent. So you cannot use always medical physics diamond dosimeter so effectively than TL dosimeter. It is a gold standard is still the TLDs, not diamond. And ion chamber. You can use ion chamber as well. And in medical dosimetry, you can use OSLD. But as I also mentioned, the aluminum oxide is not tissue equivalent. You have to correct that. The effective Z, the effective atomic number of aluminum oxide is not same as effective atomic number of tissue. So it is not tissue equivalent. Same as a diamond dosimeter. I've shown the first picture. You have to correct that. You can correct that if you know the energy of the beam, which is done in medical physics, where you are using same type of photon beam. But if the beam is mixed field unknown, then it is very difficult. It violates the cavity theory. But diamond dosimeter is not properly used, not because of expensive, but all those problems.
Right. Oh, there is a question by Raghavan, Chitra Raghavan. Could age also play a role in the female being at radiological risk than the male pilot?
Yes, it's a very touchy subject because I have got a friend, an Australian friend whose wife is a pilot, and she liked to smuggle those. At that time, I worked with the bubble detector. I have to smuggle this bubble detectors for neutron with a lipstick, and she got big problem from Union. No, Union wanted the female pilot to carry a dosimeter, but Qantas doesn't. I should tell the name. The airline will not allow that. So it was very risky. It is same in German pilot. I should not disclose her name. And she hid that in a pocket in a male pilot. The airline company doesn't know the dosimeter. They don't like the people carrying dosimeter, and female pilots is much more sensitive than male pilots, same as female astronauts.
Harish, why does
Yes, male and female.
Gender. Of course.
Yes, because female.
Have you addressed this before?
Yes, because different hormonal conditions. Not only also young female pilots are more sensitive than elderly ladies. Hormonal condition. Radiation effect is also hormonal effect. And remember, we are talking about very low dose, not lethal dose. And the very low dose creates second cancer. And it depends on the hormonal condition.
Varun Sheel, chairman of Science Division, he's asking what are the typicals of the space dosimeters?
Less than few milligram. Now I'm working with Digantara people. I've sent with them from proton dosimeter. It's got 3 milligram, and this space dosimeter encapsulation is heavier than dosimeter itself. This encapsulation is done with a tissue equivalent plastic. So that will be more than 3-4 milligram. Dosimeters are very light. The encapsulation will be very relatively heavy. But we have Dr. Digantara, we have sent lots of, we're planning to send dosimeter in space very soon. We will also develop dosimeter for biological satellite. So biological response.
That the last question. That looks the last question. So I thank you, Dr. Bhaskar, and I hand it to our dean, Professor Pallam Raju, for the concluding remarks.
Yes, thank you, Dr. Banerjee, and thank you, Dr. Mukherjee, for this really fascinating talk. I was, really amazed, by the way, you build dosimeters and the way you have built it up, and then applied it to various, various scenarios, and then carried out a lot of, tests, and you are showing very fascinating, very interesting results. I have, a couple of questions of my own. If you, I know that's a little bit late for you. Is it okay if you can? We can.
Yes.
Yes. One question. I think our talk reaches, to several people outside. So I think I got a phone call from one of our senior, colleagues, Dr. SP Gupta, who has, by the way, done a lot of balloon experiments. So he's asking. He was curious to know whether. Do you see any effect of thunderstorms on this high energy particle that you received, okay, in your dosimeters?
It is very important. We like to find out that we like to have a thunderstorm effect and also aurora australis. So if we get a chance, our balloon is very inexpensive, but organizational problem because we have to Federal Aviation Authority, you have to find out the permission.
Yes.
And it is a very important issue, thunderstorm effect. Yeah. Wow. And thunderstorm effect in space weather, there is a relationship as well.
Yes.
But we have launched the balloon in the dry, cold weather to get easily this balloon. And I have not mentioned our second balloon was 162 kilometers apart, and it took us 2 days. And we have taken help of Aboriginal trackers. They found this balloon. Very difficult to find out, but we are planning to have this thunderstorm effect. Yes.
Okay. One of my questions is that, especially when you mentioned about space weather, there have been studies which showed that, cross-polar airlines, the pilots and then the crew of airlines gets, more dosage, when they go to the auroral ovals, in this cross-Atlantic. So,
yes.
So are there any, because you have enough data there, so is there any modeling done of that, simulations to really, because you talked about the Cucinato, paper.
Yeah, but there is space dosimetry, but I have measured when I've flown to Australia, to Europe, to North Pole.
Yeah.
And
Okay.
you can see some on the paper. We have measured through equator and through pole.
Yeah.
Same time, same day.
Okay.
And it is already published. You can tell the gentleman I will send all this paper. And we found he's right. When you go over the pole, you get a much higher dose than when you go to the equatorial region. So India, it is not a big problem because we are in the equatorial region. But Northern Europe, it is very difficult, very, very, very complicated. And we are ignored in Southern Hemisphere. From Sydney, we have flown to Cape Town, completely near the South Pole. That we have compared Sydney via North Pole to Rome and Sydney to Cape Town. And these results are already published, and you can see very interesting results.
Yeah. Yeah, that's with the emerging field of space weather, it's really interesting and amazing and required to know what is
Yes,
the message.
it is done in Europe very widely, lots of universities, but India, we are not doing so much. Europe, there's particularly university in Denmark, Northern Hemisphere, they're doing all the time.
Right.
So I'm lagging behind. But we are the pioneer from Southern Hemisphere.
Yes.
Nobody has done in Southern Hemisphere, but it could be done in India as well. But we are not in the polar region. We are in the equatorial region in India.
Yeah.
Even if Tibet or Darjeeling, it will be still not as high as in Germany
Right.
or in Sydney.
Yes.
What I'm interested, this space mission, that could be done, but space mission is completely ignored. In India, lots of public relations done, but nobody cares about the human radiation effect on human. And maybe one day India will have a space station. It could be few Gaganjan will be coupled to make a space station.
Correct. Right.
But anyway, I'm focusing on space dosimetry in a small scale and maybe collaboration with your lab.
Okay. It was very interesting when you said 1889 was the first balloon launch from India for cosmic ray studies, and I didn't know that. It's very interesting to know. In fact, the founder of PRL, Professor Vikram Sarabhai, started off his research with cosmic rays, and
Yes,
that was one of the initial fields of PRL, along with atmospheric sciences in
yes, I
PRL.
know.
So it's really so we could find that kind of relationship also with you in this manner.
And Professor Baba did the electron positron, Baba scattering and molar scattering.
Yes.
He is a pioneer in cosmic. He could positron. He was the inventor of the positron.
Yes.
Professor Baba.
Yes.
But what I'm interested and we can do lots of space dosimetry coupled with medical dosimetry with the Chennai hospital. It will not be BRC cyclotron, it will be Chennai. It is made for medical cyclotron. And if you have contact with medical physicists, all the space medicine could be done in Chennai.
Yeah.
With this Apollo hospital.
Yeah. I think we have really at least shown several of us, to me definitely, that there is the various wide applications that you are able to see or witness in space dosimetry, medical dosimetry, and applied to the humans, and also going to space missions in the futuristic. It's really been a wonderful talk, wonderful hearing from you. And on behalf of PRL, I really thank you for this wonderful piece of information, and I'm sure several of us will get greater insights into this. And this is an emerging field and a lot of futuristic in nature. Yes,
I'll be delighted.
Yeah, I'm also really excited, and probably we'll have once when you are here in India to visit, and once the COVID situation is out, probably
Yes.
we have more discussions.
And I'll be visiting my BRC friend in Calcutta, but my friend's already retired, so I have got no real connection. I've got only with Professor Devabrata I have contact, and my very young friends, they are my students. But I'll be happy to work because more physics rather than all the BRC is more complicated because of nuclear facility. I try to avoid that. And please contact the Chennai hospital. This is the best. And all the equipment I tried to build myself because I'm actually, because of my engineering background, and 4 years I was as a electrical fitter in Germany.
Oh.
Really German fitters. So just like a not completely blue collar worker. And then I started studying physics. And then I developed all my scattering chambers, everything I developed myself. I can develop more practical things than the Germans.
I think your whole scientific and research career is really motivational. It's really motivating.
Thanks so much.
Thank you.
And I'm also sending some dosimeter with the Digantara friends to space. If they get a chance, they will be sending in this nanosatellite. That result, if possible, we'd like to present with you first. Space dosimetry, the homemade proton detector.
It will be really exciting and wonderful to see results in that regard. I really, on behalf of all of us, I wish you the best, and the Digantara, your colleagues, and all the best for that new experiments. And I would like to, once again, thank you for sparing your time and taking this effort to talk to us and share this amazing piece of knowledge with all of us. Thank you very much.
It's a pleasure and inspiration. Thank you, sir. Thank you very much. Thank you, everybody.
Yes. Yeah.